Okay, I'm just hoping the slides have temporarily disappeared, but I'm going to get them back. Okay, so let me introduce the next speakers. So this is going to be a merge talk, and we're going to have two speakers, Eddie and Silas, and Eddie's going to start. Go for it.
Hi, good morning everyone, and welcome to this talk on circuit transformations merged with qubit routing. I'll be talking first, so let me introduce the problem. As theorists, we may have some expectations when working with circuits. We usually work with a general circuit model where we can perform 2-qubit gates anywhere. But here we're going to take one step closer to reality and say, well, maybe some 2-qubit gates may not actually be possible. Like, for example, in the superconducting architecture where qubits are connected in some nearest neighbor layout. So we represent this architecture as a graph where the qubits are nodes and the edges represent the interactions that are possible. So for example, we can perform the unitary U1 between qubits 5 and 6 because there's an edge, but we are not able to do the unitary U2 between qubits 8 and 2 because there's no edge. So now the question is, how do we find an algorithm that, given a quantum circuit, can produce an equivalent quantum circuit that satisfies these architectural constraints? But also, we want this new circuit to be produced efficiently, so that means in polytime and polyspace. And this new circuit should not be much larger than the original circuit, either in depth or size or whatever metric you're interested in. So how can we do this? Well, let's say we are given the circuit on the left before the transformation. We can just insert swaps in some trivial manner, and then it would satisfy the constraints that are imposed here. So here the constraints are nearest neighbor on a path. And you can see that the circuit after the transformation is much larger than the original one, as maybe you would expect with such a trivial approach. But let's call this an architecture respecting circuit transformation. Basically, that is a mapping to a new quantum circuit that obeys the constraints and also preserves the original function up to some permutation of the qubits. And you may already be familiar with some of these circuit transformations. Like there are some handcrafted algorithms known for Shor's algorithm, for example, on the path graph, quantum Fourier transform on the path graph, or maybe adders on grid graphs. But we're interested in some automated approach that would work for general circuits. There's also exponential time algorithms that use SAT solvers, temporal planners, or satisfiability modulo theory. Of course, we're looking for polytime algorithms in the worst case, so we're going to keep looking. But unfortunately, it's QMA complete to even decide whether a circuit equals the identity circuit. So there's probably no hope for us to find the optimal solution. So of course, what we do is we turn to heuristics. So one heuristic that's very common is to break the circuit into sets of disjoint gates, which we call layers. So here we group the circuit into 3 layers, L1, L2, L3. And then what we can do is do the following circuit transformation, which is just execute as many gates as possible and then permute the qubits so that we can execute more gates. And there's many papers that do this, and we'll do the same. The real question here is, how do you permute these qubits? So we divide this into 2 subproblems. The first being where to move the qubits, which we call qubit mapping, which was shown to be NP-hard. And second, how to implement a given permutation, which we call qubit routing. And the routing can be achieved using sorting networks, as shown in previous work, but this can be suboptimal. All right, so let's look at qubit routing first, which is the start of our Maryland contribution. On the left, we have sorting networks versus our new approach called with the routing number. And we can see that for the path graph, we do not have much of an advantage. But for the complete graph, we go from an asymptotic circuit depth of logarithmic in n to a depth of 2. So we can obtain some asymptotic advantage in the case of routing. And why is that? So let's zoom out a little bit. We are able to simultaneously perform swaps at a matching in the graph, and we want some way to implement a qubit permutation, where the permutation is given So that's the critical difference with sorting. So this matches to a problem from computer science called routing via matchings, where we're given a graph G and the permutation pi, and we wish to find the minimum number of matchings that induce transpositions for implementing pi. And we say that the routing number is this minimum number of transpositions. And this very clearly maps to what we want to do, which is qubit routing. We just replace transpositions with swaps, and that gives us a minimum depth swap circuit to implement pi. And in the paper, we also look at token swapping, which minimizes the total number of transpositions instead of the depth, and thus gives us a minimal size swap circuit for implementing pi. All right, so what we do is we extend this, the known theory here a little bit to generalized hierarchical products of graphs, which may be best illustrated by a simple example of two path graphs. So we have a path of length 2 and a path of length 3. And we have the Boolean vector 1, 0, 1, which indicates where we have a copy of the path of length 2. So we can see that the path of length 2 connects the left side and the right side, but not the center, because we have indicated a 0 in the second position of V. And we can create many different graph products in this way, such as the Cartesian product of graphs, which may be of interest for grid layouts or grid architectures. And also what we're interested in is modular architectures, which consist of many interconnected smaller quantum processors. And we show an polynomial, no. We show an upper bound for the routing number of these graphs, and we give a polynomial time algorithm. So this upper bound is in terms of the number of nodes in the graph 2 divided by the Hamming weight of this vector V times the routing number of G1 and G2. And we actually show a slightly tighter bound depending on pi in the paper. And this, when we look at the prior work on, for example, Cartesian products of graphs, this matches their best known upper bound for these special cases. So now we want to know how well does this actually perform in practice. To do that, we first need to solve this qubit mapping, and of course return to heuristics again, because this was NP hard. So there's many strategies you can mix and match here. You can try to place gates by highest or lowest cost first for some cost metric. We can constrain ourselves to maximum matchings. We can try to place as many gates as possible, but this may come at a high cost. We can optimize for depth or for size using routing via matchings or this token swapping. We can use look-ahead to try to see where we want the qubits to be in the future, but that's very expensive. And there's two specific examples that I want to highlight here, which are the simple size optimizing mapper that we built, which just schedules the lowest cost gate at its cheapest location, that's all. And then the second one is the incremental depth mapper, which does a similar thing, which it schedules the lowest cost gate only, and then it also moves the remaining qubits a little bit closer without increasing the cost. And we compare our results with QuizKit, which is an open software tool for quantum information. And QuizKit has a circuit transformation. And we also propose a greedy algorithm, which we call the greedy swap circuit transformation, which is quite fast. This just inserts, it greedily inserts swaps on edges that bring qubits closer that are involved in some gate. It's very straightforward. So let's look at some results. Here we're looking at the depth performance on for random circuits on the grid architecture. We actually do weight gates according to single qubit gates. We weight with weight 1, C-naughts with 10, swaps with 30 to more accurately represent the empirical cost of inserting swaps into the circuit. So this is a weighted depth. yeah, and we can see that the incremental depth algorithm, which is indicated in the red line, so that's TF d comma incremental for depth incremental, seems to asymptotically perform pretty well up to a certain size, at which point it becomes too slow. And then we don't have any more data, so then what remains is our greedy algorithm called the greedy swap circuit transformation, which takes over all the way up until the largest circuits we threw at it. And we can compare to Quiskit's circuit transformation, which that seems to perform somewhat poorly on this example, which is given in orange. Second, we have a size comparison. So this is the size performance for random circuits on modular architectures. Here, our depth algorithm, maybe not very surprisingly, performs very badly because we're optimizing for size here. So our depth algorithm here is actually the worst out of the bunch. But instead, if we look at the very simple size optimizing algorithm I showed you a few slides ago, that one performs the best up until under 20-ish qubits, at which point it becomes too slow. And then, again, we have our greedy algorithm, which takes over all the way until the end. All right, so to conclude, we introduced this routing via matchings problem formulation for qubit routing, and we introduced new algorithms and generalized bounds for this routing via matchings. And then we showed the empirical performance of our algorithms for certain circuits and architectures. And this software is available freely online and is open source. And in the future, we would like to know whether swaps really are the best we can do for this qubit routing. There might be other ways we can improve on this. We may want to generalize this simple graph model we have to weighted graphs, for example, to model noise better. And perhaps we want to improve the speed or improve the performance of our algorithms. All right. So let's switch.
Great. Thank you very much. Hello. Can you all hear me? I work for a company called Cambridge Quantum Computing, and we do lots of different quantum software work. And I'm going to be talking in particular about our quantum compiler ticket because the routing solution is something very pertinent to that. So we consider a ticket to be language and platform agnostic.
You should put your mic on your shirt instead of
Oh, sorry.
Closer to you.
That good? Yeah, that's better. Cool. So we consider ticket to be a language and platform agnostic retargetable compiler, which makes our interest in solving this problem quite obvious, I think. So as Eddie said, we have an input circuit, and here I've got a simple example. And we have a graph, and we want to make sure that every 2-qubit gate in this circuit obeys the graph constraints. Eddie kind of referenced several different methods. I'm just going to go through our heuristic approach. So we have, the first thing we want to do is we want to place our qubits on our graph. And our approach for this is pretty straightforward. We want to create a graph where our nodes are qubits and our edges are interactions. And then we want to lay this on top of the architecture graph we've been presented with. So in the first layer of gates, it's pretty straightforward. We create an edge between qubits 0 and 2, and an edge between qubits 1 and 5. And we repeat this for the second one. We add a new edge between qubits 4 and 0. And then only in the third time step do we hit our first problem. we'd like to add an edge between qubit 0 and qubit 3, but we found in practice that placing an actual graph on top of the architecture graph we presented with wasn't as good as just creating these small lines of qubits and placing them on top afterwards. So we don't add that edge. And similarly, we don't add an edge between qubits 4 and 2 because we don't want to create loops, we just want to create lines. And it's just the whole process. And then we find in practice in this circuit that these are the only 2 lines we want to place onto our architecture. So we lay them on top of our graph like so. And this is our original qubit placement for the rest of the algorithm. So you can see here that those original layers now, they respect the placement, and we can execute them, and we can remove them, and then we can move on. And you also see that we didn't place our 3rd qubit on our graph to start with. That's because it wasn't in any immediate interactions, but when we find an interaction using it, then we'll place it, which happens to be for the circuit I showed you right now. So we find the node qubit 0 is on, and in this case, that's the one bang in the center, node 4, and we try and place qubit 3 next to it. And in this case, we've got a free node at 3, so we add it there. If there wasn't a free adjacent node, we just find the closest one possible and add it. Like so. And that's that. So that's our initial qubit placement done, and from here on, we're just adding swap gates to our circuit to make sure it respects the architecture. So you'll see here, we have swap gates. We've got CX gates we'd like to do between qubits 2 and 4 and qubits 0 and 5. Neither are possible in the current placement, so we need to modify it, which is obviously done by adding swaps. So we do this by creating new placements which are only single swap away from our original placement. And we do this by, so we've got these 4 active qubits, and we do this by generating what we like to call candidate placements, which are created by one single swap along each of these live edges, which are each connected to a live qubit. So in this case, we're going to take 6 candidate placements, and we're going to put them all into our heuristic and compare them. Here's an example of 2 of them. One is a swap gate between qubit 0 and 2, which is P1, and one is a swap gate between qubit 0 and 4, which is P2. And you can see the red lines are showing how the distance between interacting qubits is changing. And so you might notice there that P2 is looking pretty good. So we give our heuristic these 2 placements and the first layer of the circuit, and it assigns a distance measure to each of them, and it selects the best one. And here it's pretty obvious which one's better because our P2 actually solves the problem. So we pick it. We add this chosen swap gate. In practice, we'd have compared all 6, but we don't really have time for that now. But we add our chosen swap gate, we update our placement, and we execute all the gates which are now possible. So we've changed our current global placement to the one on top right now. Let me get rid of some gates. And actually, we can get rid of a CX gate from the next layer as well. So we kill that. But now we'll see qubits 2 and 3 aren't on adjacent nodes, so we go again. This time, there's only 2 interacting qubits, and each one only has 1 live edge. So we've got 2 candidate placements, swapping along 2 and 4 and swapping qubits 3 and 4. But we can see if we do either of these that they both solve the problem for the first layer. There's no obvious preference, so what do we do? And the solution is very simple. We introduce a very basic look ahead where we complete the same heuristic, but we consider the second layer of the circuit instead of the first one. So you'll see here this P1 actually solves it for the next layer, so if we add it to a heuristic, it's going to opt for it. So we apply the swap gate, and we update our placement, and we execute all the gates, which are now valid, etc. And this is essentially how the whole algorithm works. It keeps on going like this until there are no more CX gates we need to satisfy. So we can say it's solved now. We had our original circuit at the top, and we've produced a rooted circuit, which is at the bottom. And this respects our graph G if our initial placement is that one on the left there. And that's basically the whole algorithm. And we found in practice this works pretty well. So we've completed a bunch of synthetic benchmarks, we call them, for some kind of typical architectures you might expect in a near-term quantum computer, such as the square grid and the ring. And we compared the scaling. I don't have any asymptotics here, but if you are interested, there's a paper, you can go look at all of them. What I think is more interesting is our benchmarks against other compilers. So we use a set of 156 circuits, which are available in our paper. So if you're interested, you can find them there. And we compared on 2 real architectures, both by IBM. One is the IBM QX5, which has got 16 qubits, and one is the IBM Tokyo, which is 20 qubits. We ignore single gates because we're only caring about CX overhead. We completed them on the same Google Cloud machine, 1 hour compute time circuit. And we compared ourselves to, well, ourselves, IBM's Qiskit, Rigetti's Quill, and Project Q. And we do a full benchmarks and table in the paper, but for now, let's compare our results. This is just the ticket solution, and we find that we have a linear scaling across our entire data set. And in particular, we can see that the scaling is a bit better for the IBM Tokyo device, which makes sense because it's a better connected graph overall. And this is the kind of same overhead in CX depth and CX count. I think there's a more interesting graph where it compares us to the other competitors. And we find that Qiskit, Quill, and us seem to have a linear overhead, while in fact Project Q's results might be doing something a bit different. And actually, on the right, we can see there are no Project Q results because they weren't able to actually compute the circuits for this slightly more complicated architecture. But in general, we find that actually comparing across all these systems, the ticket's coming in just at the bottom, so same scaling, but our constant's a little bit better, which is good for us. And we also find there is a similar pattern with the depth and not just the CS count. In this one, it's a bit more competitive between us and Quill, in particular for the IBM Tokyo device, but overall, we're at the front here, which is good for us. As a summary, so as a description of our algorithm, we create these lines of qubits, we place them on our graph, and this is slightly greedy. Every time we update our placement, we dynamically reslice the circuit, which makes sure that every swap gate we add is as effective as possible. It's a relatively cheap heuristic, which is nice, and also we use look ahead as a tiebreaker if we've got two placements that are affecting the circuit in the same way. And what do you get if you do this? We have a linear routing overhead, beats all the current competitors on CX count, at least the time of releasing the paper, in the ballpark for best CX depth overhead. And also, it's incredibly computationally cheap. It goes through circuits in seconds, so you can run circuits which other competitors might not be able to. And I guess the other part is what we think of doing in the future. So we're using CX depth and CX count as a metric here, because if you're going to be routing a circuit, if you're routing a circuit, it's because you want to run on an actual device, and these are kind of important considering the noisy era we're in right now. But actually, going further ahead, what's our main kind of implementation focus is to bring fidelity information into our picture. So it's something we might consider called fidelity-aware routing. And this is something Eddie mentioned as well, actually, with an idea of putting weights on edges or putting weights on nodes and prioritizing certain parts of your graph which are better. That's pretty much that. So as a reminder, pip install PyTicket if you want to try it out, it's all there. And also as a company, we are always looking for new hires. So feel free to contact either me or Ross there if you've got any questions about anything. And that's it.
Thanks so much for the talks. All right, we have time for questions. So please raise your hand or in some other way draw my attention. We have people standing by with microphones.
So for the second talk, do you have any limits on the kind of graphs that your tool will work on?
No, as long as it's connected, we can take any graph type. Yeah.
And have you done any tests of like speed performance as the graphs become more complicated?
So if you look at the synthetic benchmarks in our paper, you'll see that we slowly increase the size of the architecture. And I believe there is timing results there, but I couldn't give you an accurate number right now. But all the information is there if you're interested.
Okay, thank you.
Any other questions? Nope, go on. Last chance. Nope. All right. Okay, let's thank our speakers again.